to have also a pulsar, which was the origin from the radiation. In 1969, Jerry Fishman began his professional career as senior scientist working on aerospace projects at the research laboratories of Teledyne Company in Huntsville, Alabama. And well, I think you got position with 1 week delay, you told me, because he went to the interview 1 week after, and he was lucky enough that he got the position there.
They hired him anyway.
Yeah. And I think it's worth to point out that this research operations center was instigated by Milton Cummings, from which the Cummings Research Park, the second largest in America, is named nowadays. Fishman joined NASA at the Marshall Space Flight Center in Alabama, Huntsville, as a research scientist in 1974. And from the very start, he worked in high-energy astrophysics, and namely in gamma ray astronomy. During 78-79, Fishman took an assignment with NASA headquarters as a staff scientist in the astrophysics division of the Office of Space Science. And upon returning to Marshall Space Flight Center, he continued his work in gamma ray astronomy, and he became principal investigator of the Person Transient Experiment, Solar Experiment BATSI, which was one of the main instruments on board the Compton Gamma Ray Observatory, which was the second large observatory of the NASA program following famous Hubble Space Telescope. And this observatory, Compton Gamma Ray Observatory, was launched in 1991 and was intentionally decided to went down to the Earth, and it's, I think, in the bottom of the Pacific Ocean in year 2000 when one of the gyroscopes failed. So during these basically 10 years, BATSI detected, I think, more than 2,700 gamma ray bursts, which was a major breakthrough in the field, because this gives clues to the nature of the events, together with multi-wavelength observations by other observatories such as Bevo-Sachs. I still remember that when we met for the first time in 1993, the second Huntsville JP workshop, I was one of the 300 guys sitting in the audience. I don't remember if it was you or was Bill Pachesas who took the microphone and asked who of the guys in the audience thought that GRBs were of galactic origin. And then I think about 10%, 30 people, me included, then rose our hands up. Yes, because we thought that they were of galactic origin. And then who think that GRB are of cosmological origins? And then another 10% of the people rose hands up. So 80% of the people, they had no idea of the origin of the events. So nowadays, and thanks to BATSI and to Bevo-Sachs, we know that they are of cosmological origin, that they are related to the largest and most energetic explosions in the universe. And this was one of the major discoveries in astronomy in the 20th century. And for this research and this discovery, both Enrico Costa in Italy and Jerry Fishman here, they were awarded with the Shaw Prize in year 2011. Enrico Costa told me that when he got the email with the Shaw Prize award, he thought that it was a spam, because I think the email started like, "Do you want to win $500,000?" I think Enrico Costa, I think he told me that he wasn't really going to send the email to the spam. But I think then he continued reading, and probably it happened to you too, and then it was true, it was not a joke. So the community, GRB community, we are very happy when we knew that both Enrico and Jerry were awarded with this, also called Asian Nobel Prize. So I think I shouldn't tell you anything else. I prefer that Jerry will introduce you to the origin or early story of gamma ray bursts. He really has been a main actor in this field, and many scientists in the Institute, starting with me, who was the first guy who started GRB in Spain, and with the rest of scientists who are here together, we have benefited so much of the initial work you have carried out. So thank you so much.
Thank you. Thanks, Alberto. Okay. Oh, okay. Sound. And we're going to cruise around, make 6 stops in Spain, and end up in Lisbon, Portugal. This is next month will be our 50th wedding anniversary, so it's a very special time for my wife. So let me say hello to my wife Nancy, and it's great to be here. Now, this was the title of my talk, but instead I'm going to change it a little bit. I'm not going to talk so much about the early history, because the early history you can find in these 3 references. They're very good. This one is flash, and I'm going to leave this book here for you. You already have one in the library, but here's another copy. It goes into the early history of gamma ray bursts. Number 2 is a DVD made by Nova, and they gave it a sexy title of Death Star, because a lot of people think that the gamma ray burst will sterilize the Earth and cause destruction of civilizations and different stars throughout the universe. So they call it Death Star. And third, there's a very good presentation by Bill Pachasis, a good friend that you mentioned. He was one of the helpers in the first Gamma Ray Burst Conference in Huntsville. An old colleague. He was the 3rd person to join the Gamma Ray Burst group in Huntsville. Huntsville is not known for its scientific expertise. Instead, it's known for rocket propulsion primarily. The primary astrophysics group of NASA is at the Goddard Space Flight Center outside of Washington, D.C. But in Huntsville, we have about 80 or 90 scientists that not only do astrophysics, but also there's a lot of earth science. So instead, I'm going to give you a personal journey, some of my own personal experiences in the early days that got me here and got me involved with the Batsy experiment, which was my primary work that I did while I was with NASA. I'm now retired from NASA. I've been retired for 3 or 4 years now, and I was very fortunate to get an emeritus position. They just started an emeritus designation for a few people in Huntsville. Okay, well, believe it or not, that's me when I had hair. Right there. This is me as a graduate student at Rice University, and my advisor, Bob Hames. We put together a balloon flight program, and Alberto mentioned this, and this was the best way of doing science. The first one in your field to do gamma ray astronomy between the energy of about 50 kilovolts to 1 MeV. And it was, there's an old expression in the US of shooting fish in a barrel, which means that it's a very easy thing to do, because almost every balloon flight we had, we discovered something new. It was the Crab Nebula, then it was, we found gamma rays for the first time from the galactic center above 100 kilovolts. We found gamma rays from the nearby active galaxy Centaurus A. And a few other objects, so it was easy pickings. Since that time, gamma ray astronomy has become very difficult. Once you go to the next level of gamma ray astronomy, the photons are few and far between. It's not nearly as easy as X-ray astronomy, where you can focus the X-rays. You cannot focus gamma rays. You have to use special detectors, and it takes a lot of high atomic number materials, scintillation detectors and germanium detectors to stop gamma rays and to shield against the ever abundant cosmic ray background. It's very analogous to try to do optical astronomy during the daytime. Your signal to noise is 1%, if you're lucky, 1%. So you have to look at the background just as much as you look at the object. And you have to go back and forth from background to object and subtract the two to get your signal. Right, Alberto? He knows about it. In fact, you were involved with some early balloon flight observations, were you not? In the early time. Okay. So anyway, that's us. I remember asking my advisor before I came down to Rice University what type of research is going on at Rice University. He says, well, I'm starting up a program in balloon-borne gamma ray astronomy. So after I hung up the phone, I went to the library. I tried to learn more about gamma ray astronomy. I couldn't find anything. All I could find is X-ray astronomy, but no gamma ray astronomy. So I said to myself, that's for me. You get in on the first observations of gamma ray astronomy, and I'm glad that I did. Let me just go back. My colleague, Bill Pachasis, let's see, is that? Yeah. He has a number of slides that, did I email those to you? Mm-hmm. He has a PDF file. So if you want to delve into the early history of gamma ray bursts, look at these slides. He actually taught a course at the University in Huntsville on the history of gamma ray burst astronomy. And he's got an excellent set of slides that he kindly gave to me and said that I could pass them on to you if you wanted to. Let's see. Okay, this is getting ready for balloon flight to observation. We had our detector system up here. We had an optical sighting to make sure that we were looking at the radioactive source off in the distance. And this is the gondola that's carried up to 120 to 130,000, about 40 kilometers. You have to get up to 40 kilometers to get over 99%. Above 99% of the atmosphere. You can't do gamma ray astronomy from the ground. You can't even do it from aircraft altitudes like you can infrared astronomy. You have to go way up there. You have to go up to 35 or 40 kilometers to be able to see the objects. Hit the wrong button. Well, just a balloon flight sequence. This is a gondola similar to the one I showed you on the last slide. Here the balloon is being inflated. This is only about 5% of the balloon right here. The other 95% is laying on the ground attached to a parachute. You can see the parachute here and the special launch vehicle holding the gondola and the payload. Then they release just the top part, just the bubble. It's $25,000 worth of helium just to inflate that. And then they let it go. Most of the balloon is uninflated at the surface. As it goes higher and higher, it keeps getting more and more inflated. And here's a picture of it at float altitude where it's fully inflated. This is about a 40-story building from here down to here, 40 stories. It costs, most of your money is in blowing up the balloon and the balloon itself. Of course, as it goes up, it expands because of the lower pressure until it's fully inflated. And it's called a zero pressure balloon because if you have any pressure in there at all, it'll burst. So they intentionally let the excess helium go out of these vent tubes that are hanging down. Otherwise, it would pop. And there's a parachute. And then finally, when you finish your observations, you send a signal to it, and it fires an explosive device that cuts the parachute loose. The payload is this little dot here hanging on. And then if you're lucky, and we were very lucky, we recovered our gondola with very little damage, and we refurbished it and flew it again for our next observation. So as Alberto mentioned, I did this work at Rice University in Houston, Texas, and then I moved to Huntsville, Alabama, to work on the HEO program, High Energy Astronomy Observatory, during the 1990s, which was canceled, and then it was reinstituted as a much smaller program. HEO was originally 4 very large spacecraft on a very large rocket, a Titan III rocket. They're in the Nixon administration of the U.S., the budget was cut down. They had to cut it down from 4 spacecraft to 3 much smaller spacecraft. Each one was about a third of the size. And Alberto's advisor was a principal investigator on one of the cosmic ray experiments of the third HEO mission. And so I was hired to act as a scientific liaison between the engineers and the principal investigators. Okay, well, most of you know this early history. In 1969 is when they first started seeing these gamma ray bursts with very small detectors about the size of a coffee cup on the corners of a spacecraft, Vela spacecraft. They were launched 2 at a time on a rocket. I believe it was a Delta rocket, and I think there were 12 or 15 of these spacecraft that were operational. These were not secret spacecraft, but their capabilities were secret. They were, the exact capabilities were secret, but their purpose was to look for clandestine thermonuclear explosions from the Russians or the Red Chinese who might try to cheat on the test ban treaty that was in effect and set off thermonuclear explosions in space or even behind the moon. They actually thought that they might try to fool us by setting off thermonuclear explosions as a test behind the moon. So they launched these series of spacecraft to even have very elliptical orbits and look behind the moon so they could see if the Russians were cheating on the test ban treaty. And of course, they never found any of this cheating going on, but they started seeing every once in a while, they would see a burst of gamma rays. Now, they had all kinds of detectors. They had optical, gamma ray, X-ray, and infrared detectors on the spacecraft to look at any kinds of radiations from a thermonuclear explosion, but they didn't see any. Instead, about once a month, they would see a burst of gamma rays over here and then over there. They had no idea what it was, and they weren't coming from the Earth. They weren't coming from the sun. They weren't coming from anywhere in the solar system, Jupiter or anywhere else. They were a complete mystery. They remained a mystery for many years. Other spacecraft besides Vela started seeing these, but none of the other spacecraft were designed to look for gamma ray bursts. They were designed for other things. Even the famous Uhuru X-ray satellite, the first X-ray satellite that the U.S. had in orbit, they started seeing these gamma ray bursts at random. Each one of them had a little different duration. They had no idea what it was. Then models started coming out with gamma ray bursts. It was one of, as Alberto said, it was one of the major mysteries of astronomy in the past century. So after I came to Huntsville, I said, well, maybe if we had bigger detectors, instead of seeing them once a month or so, we would see them much more often. So since I had a balloon background, I said, let's try to build up some large detectors, and we'll see them maybe an extrapolation of the -3/2 power law that you would expect would say that you should see maybe as many as 20 of them in a day. And a balloon flight lasts anywhere from 12 to 24 hours. So we had a good chance of seeing a lot of them in one day. So we had a couple of balloon flights. And these were very cheap detectors. They're actually scraps of sodium iodide, which was our preferred detector material. And as I mentioned last night, we tried to save as much money as we can. We even used beer cans to cover up some of our photomultiplier tubes to shield from other electromagnetic radiation that might be affecting the photomultiplier tubes. And we put together a gondola very inexpensively, because this was what do you call it? Sort of a backroom experiment. We really weren't funded to do this, but we really wanted to do it. So we built up this group of detectors to fly, but we only saw like one. We only saw one a day instead of 20 a day. So this was already showing us there was a deficiency. And I remember presenting this observation at a conference in Los Alamos, and they thought, well, something's wrong with my system, and I really should have been seeing 20 of them a day if they're really isotropic, but something's wrong with my experiment. So people really didn't take notice of it, except for one guy. There was one guy who came up to me after my presentation, and he says, oh, Jerry, let me find out more about your detector system. And that person was the well-known astrophysicist, theoretician, Bohdan Paczynski. It was Bohdan Paczynski who was kind of the voice in the wilderness. Everybody thought they knew the answer. Well, these gamma ray bursts, they're coming from neutron stars. There's something about a neutron star. Brad Schaefer wrote a article in Scientific American. He says these are caused by neutron stars. Either there's a comet that's impacting on a neutron star, or maybe it's two neutron stars merging. Something is or a crust quake in a neutron star. A neutron star is supposed to have a very tough crust, and if that crust quakes, like an earthquake or something, it would produce a gamma ray burst. Everybody was convinced that they were caused by neutron stars within our galaxy. Well, in '77, there was an announcement of opportunity for a gamma ray observatory, and Alberto said GRO was the second of the 4 great observatories in space. And I think I mentioned this last night, that people at NASA headquarters were very smart in packaging this as the great observatories in space, and going to the United States Congress and asking not for 1 spacecraft, but for 4 spacecraft, $4 billion spacecraft over the next decade to cover the electromagnetic spectrum. So they didn't have to go back every other year and fight to get money made. Hubble was already approved, but they wanted also HST was already approved for the optical region. GRO was the second one. Chandra X-ray Observatory was the third, and CERTIF was the fourth, infrared astronomy telescope. So it was to cover the entire electromagnetic spectrum with unprecedented sensitivity. And so we thought, well, with our balloon flight experience, let's go ahead and propose an experiment, but we won't call it an experiment. We're going to call it a monitor. We're going to provide a service to the other experiments on board the spacecraft. So we kind of disguised ourselves as a monitor service to other experiments, because every experiment that was proposed for the Gamma Ray Observatory had as a secondary objective their other detectors that, well, it gets a little technical, to act as anti-coincidence. We would also be capable of looking at gamma ray bursts in addition to our primary objective of studying particular objects for their gamma ray emission. Tom Klein at Goddard Space Flight Center, he called me, he says, Jerry, you know, at Goddard we can't propose for a GRO experiment because we're heavily committed to the high energy gamma ray region above 100 MeV. This was the experiment that eventually flew on GRO, the main experiment in the middle. It was a spark chamber to look at high energy gamma rays. But we said the original name of our experiment was not an experiment, it was a monitor. It was a gamma ray burst monitor. We later on changed the name to the Burst and Gamma Ray Source Experiment, BATSI. Okay? And instead of using those crude detectors, we were going to use good detectors. Let me hurry up here. So these are our good detectors that we proposed for GRO. You can see how much better they were, how much cleaner and whiter they were than the junk that we were flying, crystal pieces. These are excess materials in mineral oil, which they were efficient, but we got very poor energy resolution. But we did detect gamma ray bursts. Here we were putting some of the prototype detectors aboard a gondola, covering them with thermal insulation, and then flying them on a balloon. This is the balloon flight we had. Was done from Palestine, Texas, where most of these flights took place. A place called the National Scientific Balloon Facility. And this is iron shot ballast. We flew more ballast than we flew experiment. This weighed about 1,000 pounds. This only weighed 700 or 800 pounds up here, because we wanted the balloon to stay up in the air as long as we could. Every time the sun would set, you would have to drop about 400 pounds of steel shot in order to keep the balloon from falling, because it was a zero pressure balloon. Most of the balloon is lying on the ground right here. They only blow up this little bubble. Well, during the 1980s, 1990s, all kinds of theories were developed. And I don't expect you to read this, but the references down here in Comments to Astrophysics. Bob Nemiroff. Anybody know about the Astronomy Picture of the Day, APOD? Does anybody watch that? It's a very good site. He's the one responsible for the Astronomy Picture of the Day. Well, at the time, he was very interested in gamma ray bursts, so he went through all the literature and he found over 100 different reasons why there should be gamma ray bursts. And almost every one of them was galactic. In the galactic disk or the galactic halo. Every once in a while, later on, and after Batsy was flown, then they started coming out with cosmological models for gamma ray bursts. So I already mentioned this was the largest experiment designed specifically for gamma ray burst observations. It covered the entire sky. It was operational for 9 years. The spacecraft was working perfectly in the year 2000. All the instruments were working fine, but we lost, as Alberto said, we lost one of our gyroscopes, and NASA was very afraid that the spacecraft might re-enter the Earth uncontrolled and somebody would be hurt. So they intentionally dropped it into the Pacific Ocean in the year 2000, even though all the experiments were working at the time. It was a very, very sad time for all of us. These are the Batsy detectors. There were 8 of them on the spacecraft. They were all designed, built, calibrated right there in-house in Huntsville, Alabama at the Marshall Space Flight Center. There were 8 of them on the spacecraft. We wanted symmetry. We had an octahedron geometry, so that no matter where the gamma ray burst went off in the sky, there would always be 3 and only 3 there would be 4 detectors that would see the gamma ray burst. So we could get a position and some feeling for the uncertainty in the position with the observations by 4 of the 8 detectors. And so the 8 of them were on the 8 corners of the spacecraft in an octahedron geometry. And this is after the 4 experiments were put on the spacecraft. This was the heaviest scientific spacecraft ever launched by the space shuttle. It weighed over 15,000 kilograms, I believe, 12 to 15,000 kilograms. It was the only payload that the space shuttle carried on that particular mission. Here's myself. I still had some hair, but it was turning gray, like Alberto's, Jim Kurfus, Volker Schoenfelder from Max Planck MPI in Germany, and Carl Fichtel, the principal investigator of the Egret experiment. This was the Egret experiment. This was the Comptel experiment. This was a cover over the OSSI detector system, which is a pointed detector. And here are the Batsy detector modules before they're covered up with thermal insulation. This picture was taken at TRW, which was the spacecraft contractor. This was an $800 million experiment and the heaviest launched by the space shuttle. It was heavier than the Hubble Space Telescope. Here we're doing some calibrations with some radioactive sources. This was done for radioactive sources were on these platforms, and they were being observed by the 4 top BATSI detector modules. There it was launched April 4th. Last year was the 25th anniversary. There was a special celebration at the Goddard Space Flight. This was a Goddard project. Even though we were a Marshall Space Flight Center experiment, the entire program was run out of Goddard Space Flight Center outside of Washington, D.C. And the project scientists just unfortunately passed away just a few months ago. A very good friend of mine, Neil Garrels. And Neil was also the principal investigator of SWIFT. And SWIFT is now making extraordinary observations of gamma ray bursts, getting their precise locations in optical and X-ray region of the spectrum. Here's an actual photograph just prior to deployment. The space shuttle holds out the spacecraft on an arm. This arm is being controlled by one of the astronauts who I know fairly well, Linda Godwin, who's now a professor of astronomy at the place I went to undergraduate school at, the University of Missouri. She's an astronomy professor. It took her a year to practice. She did underwater practice of a mock-up of the entire observatory to practice taking it out of the shuttle on the special Canada arm, putting it outside. A lot of people think that they throw these payloads overboard. They don't. They just let go of them, and then the space shuttle slowly drifts away. They don't want to impart any kind of velocity to the spacecraft. And here it is after she lets go. There's part of the arm. And they had to get the solar panels facing the sun. They wanted the batteries to get completely charged immediately. So these solar panels, so she was forced to take a picture into the sun. And that's why it's such a crummy picture. But you can see her hands. She's taken this through a window, the back window of the upper deck of the space shuttle, and she's holding a camera. And if you look closely, you can see the outline of her hands holding the camera, looking through the window. The sun is illuminating her hands and then reflecting off of the window back into her camera. It's a very interesting picture. And there she is. There's Linda Godwin. She's holding up the patch. Every shuttle mission had its own patch that they wore. Here you see that all four of the 5 astronauts, you can see their patches. She's holding a large scale. The patch is unique to this particular mission. Here's the Gamma Ray Observatory. And this is STS-37. This is the 37th launch of the space shuttle. And that's Linda Godwin, who is now an astronomy professor at the University of Missouri. Well, I'm not going to go over all these. These are some of our accomplishments. We still remain the most sensitive experiment ever to look for gamma ray bursts. We covered the entire sky. And we were seeing about one a day, every day, about 300 a year, a little over 300 per year. And hundreds of papers were based on BATSI papers. We had over 50 PhD theses based on BATSI data. We saw 2,704 gamma ray bursts over 9+ years. And this likely won't be exceeded. There still is no plans for another gamma ray burst experiment with a higher sensitivity than BATSI. We're very fortunate to have the space shuttle, to have our payload capability. I'm not going to go over all these. It was pointed out last night that BATSI was not the first experiment to see the 2 different distributions, the hard spectra. They're a lot shorter duration than the softer gamma ray bursts. The Russians actually saw it, and Eugene Mazet's, it was actually published in one of his papers, that they noticed these 2 different distributions, but at the same time they still thought that they were galactic. Here's the 2 different distributions, the hardness ratio of the gamma ray burst versus the duration, and the 2 distributions of bursts showed This is from Chrissa Cavogliotto, my colleague in Huntsville, who's now at George Washington University in Washington, D.C. She's a professor there. She left Huntsville 2 years ago. And some of you know Chrissa. And here's our sky map. 2700. They're color-coded by the intensity, and you see they're isotropic. Completely unlike other distributions. Here's X-ray sources, which show the galactic plane and concentration near the galactic center. Here's a gamma ray, high-energy gamma ray, not gamma ray burst, but high-energy gamma rays. This is what the galaxy looks like, the plane of the galaxy, with the concentration toward the center of the galaxy. You see a couple of very bright sources, the Gaminga, the Crab Nebula. I think Cygnus must be on the other side in the galactic center region. Of course, the Batsy distribution. Within statistics, it's completely isotropic because they're coming from the edge of the universe. They have to be isotropic. So this is what people expected. If they should follow a -3 Hz power law. The gamma ray bursts, the brighter ones follow this -3 Hz power law. The intensity goes as 1 over the distance squared, but the number density goes as the distance cubed. And combining the two, you should get if you plot the log of the number of bursts per year, the frequency of gamma ray bursts versus a log of the intensity of gamma ray bursts, you should get exactly a -3 Hz power law given by the red line. Instead, Batsy observed a definite deviation, and this is because we're running out of the universe. We're seeing toward the edge of the observable universe, where the number density is definitely decreasing. So there's a bend over in the -3 Hz power law. Now, an earlier observation by Pioneer Venus Orbiter, the Russian experiment, also showed a slight bend over, but this is instrumental. If they would have had the sensitivity of Batsy, it would have continued to follow this -3 Hz power law. You see, this for the very bright gamma ray bursts, there are only a few of them a year, so your statistics fall away. In between, you have very good statistics that follow exactly as the redshift is much less than 1. You expect a perfect -3 Hz power law, which is what is observed. So everybody thought that in the 1970s, 1980s, there were over 100 different models of gamma ray bursts, and almost all of them had galactic distribution, because they thought they were coming from neutron stars. Some people thought they were coming from black holes within the galaxy, but they weren't. They were cosmological distances. If they were nearby in the galaxy, you would get an isotropic distribution, because you were only seeing out to this diameter where the sources are isotropic. But if they were coming from far away in the galaxy, then you would start to get the concentration in the galactic plane. If they were coming from far away, you would see this deviation from the -3 Hz power law. If they were nearby, they would exactly follow the -3 Hz power law. So if they were nearby in the galaxy, you would get this and this. If they were far away in the galaxy, you would get this and this, shown by this diameter, this volume here. If they were distant, you wouldn't get as many far away, so they would fall off. But instead, they were cosmological distances. So we had an isotropic distribution, and we had a deviation. This was the observed distribution. So it became clear to most people, not everyone, but most people says, okay, I give up, they're galactic. Some people have fudged different models to make them fit this type of a distribution. It's a very interesting classic case of astronomy, in astronomy or any other field of science. People get hung up on pre-existing notions of what it should be like, that they were galactic objects. Bohdan Paczynski was only one of the few people who thought, no, these may be at cosmological distances, and that's why we're seeing a bend over. This is why it's bending over. He was about the only one. He was a very, very bright astronomer. I think that's about it. We made the cover of Nature on 1992. This is the. I told Chip Megan that I said, Chip, you're the main leader of the studies of gamma ray bursts, so you be the first author. So if you want to make me second author, okay. So he put most of the BATSI members on his paper, but he wrote the paper. We got a reply from the editor of Nature within 2 weeks that it was accepted. We had two referees. One referee said, well, we ought to fix a couple of these things, which we did. Most of it was grammatical or something else. The other referee said, this paper needs to be published immediately. And we found out later on, shouldn't be told who the referee is, but I think it was Bohdan Paczynski was that second referee. We need to publish this immediately. So, as Alberto mentioned, I was awarded the Shaw Prize in Astronomy. This was presented in Hong Kong in 2011. Mr. Shaw, who was a movie mogul, he had several thousand theaters all throughout the Far East, in Japan and China and the Philippines and Thailand and everywhere else. He was a multi-billionaire, and he was 103 years old at this time. And his wife was 50 years younger, Mona Shaw. She was a singer. They got married in Las Vegas when he was 80 years old, and she was 30 years old. She was a singer. They got married in Las Vegas, and she loved flowers. So she was in charge of all the arrangements at the Shaw Award ceremony, and she loved flowers. So everywhere you looked, there was flowers at the Shaw Prize ceremony. And this was during my acceptance speech. And here's another, and this is me giving my acceptance speech. And here's they showed a picture of a detector module of BATSI. And I guess that's it. Let me see. That's it. I think that was, I turned it off. I'm sorry. That's it. Okay.
Thank you very much for a wonderful talk and the microphone. So I'm sure there will be a few questions.
Who wants to shout first? Okay, well, so I will start. So which sort of experiment or monitor will you do if you can get
well, it depends on what the
funding?
operational objective was. If it was to get as many bursts as we can, or the highest burst frequency, I'd fly BATSI again. If I wanted to get the exact location, I would fly something like Swift. In fact, during the competition, Swift was what they call a mid-X, a medium-sized explorer mission. It was instead of costing many millions of dollars, it was limited to I don't know, $30 million or something like that. There were 6 proposals that were submitted for a mid-X with identical scientific objectives. The objective being to get precise locations for as many gamma ray bursts as they can. I was the principal investigator in one of those, and I lost. I lost to my good friend Neil Garrels. Neil Garrels is the principal investigator of the Swift spacecraft, and he was very smart because he got some international collaborations going from UK and from Italy. very important experiments from both the UK and Italy, which has made SWIFT the exceptional satellite. It's still operational today, and hopefully it's going to be still operating 10 years from now. It's been giving all you optical astronomers a lot of precise locations and galaxies to get their spectra from and look at the afterglows. So it's a tremendous experiment, and we were really sorry to lose Neil Garrels, a good friend of mine, and he was the chief scientist of GRO. It started out to be Don Niffen, and then after we were in orbit. By the way, NASA, what they do for each of their major observatories, like Hubble, Compton, Chandra, and Spitzer, once it's declared operational, which is 1 or 2 months after it's safely in orbit, and they know it's operational, then NASA decides to honor the spacecraft by naming it after a famous scientist. And it was my suggestion that the GRO, Gamma Ray Observatory, be named after Arthur Holly Compton, who won the Nobel Prize in the 1930s. He was the one who was the first one to determine what the wavelength or the energy of gamma rays were in the 1930s. Arthur Holly Compton. So it's the Compton Gamma Ray Observatory, the Hubble Space Telescope, the Chandra X-ray telescope named after Subramanian Chandrasekhar, famous professor at University of Illinois. And he, for many years, several decades, he was the chief editor of the Astrophysical Journal. And then Lyman Spitzer, who I was fortunate to get to meet. Lyman Spitzer is the one who, I heard him give a talk when I was a graduate student at the University of Virginia, talking about a space telescope. Lyman Spitzer, and I think in the 1940s, he was coming up with ideas for a telescope in orbit around the Earth, in space, no atmospheric disturbances. And it became the Hubble Space Telescope. But they decided to name that one after Hubble. But the fourth one they named after Spitzer. Lyman Spitzer from Princeton University. Got time for a couple of questions. Come on.
Enrique?
A couple of questions. How I understood correctly from the table that you gave of hypothesis that Colgate was the first one to publish the supernovas in external galaxies as the source of gamma rays?
Yeah. Sterling Colgate, let me answer that one first. He was a very colorful fellow. I was very fortunate to know Sterling Colgate, and I was on a publication with he and Don Clayton when I was a graduate student. It's according to Don Clayton, it's one of the 100 best papers in the Astrophysical Journal of the last century. Clayton, Colgate, and Fishman. It gives, Zach well knows, this paper. I really had nothing to do with the theory. I was the only one of the 3 people who knew how to program a computer in Fortran. So I did some calculations, and Don Clayton put me on as a co-author. But this was the first paper to look at the gamma radiation from radioactive decays following a supernova, namely nickel-56 and cobalt-56. Colgate loved explosions of any kind. He made a career out of studying all kinds of explosions. And of course, the biggest explosion we know of is a supernova. So he came out with several papers on supernova, and he actually predicted that supernova should produce gamma rays in the 1960s. I remember a paper of his at the Cosmic Ray Conference in Calgary, Canada, giving a paper. What was your
my main question is related to your actual personal experience. Is how critical were these first that you choose to do your PhD with this your supervisor who was designing how to build the first experiment to detect the GRB gamma rays. And then this other back on the envelope, so-called project, which was unfunded with these very large detectors that only Paczynski appreciated the result. How critical were these two points in your history in the development of the gamma ray GRBs?
My thesis was not about even though we discovered the gamma radiation from the Crab Nebula, and then 2 years later, we went back to old data from 1966 data before pulsars were discovered. And I said, these Crab Nebula observations, maybe we can see pulses from the Crab Nebula. So Rick Harmon, a colleague of mine who really knew how to program the computer, started folding the data. We folded 8 hours worth of data, and it took many different iterations because we didn't know exactly what the period would be of the pulsar in the Crab Nebula 4 years prior to when we were doing it, when the optical pulses were discovered. So it was difficult, but finally came out. My thesis work was gamma rays from active galaxies, and I decided to study 2 active galaxies, M87 and Centaurus A. And both of them got presented at conferences, but my thesis was wrong. My thesis, I said that we see gamma rays from M87, but we don't see them from Centaurus A, which turned out to be wrong. I didn't take into account the systematic errors in that data. I was just looking at statistical errors. And statistically, we did see more gamma. But as I pointed out, the signal to noise was so low that the systematic errors are extremely important. And I underestimated the systematic errors, and it was wrong in my thesis, but they're not going to take away my PhD.
Any other questions? Okay. If not, let's thank Jerry again for a wonderful talk.
Buenos dias.